And a good embedding encapsulates the semantics, meaning that a semantic close other word, other input, like queen, has an embedding which is very, very close to each other. And as you see, some parts of these embeddings look very, very similar. And this is the power of a good word-to-vec implementation. Whereas other words, like water, which has nothing to do with king or queen, right? This exact same embedding is completely off semantically, but also from the numbers of those embeddings. So we say that the distance is high. And to make it more visualized, because those are 50 dimensions, and to imagine a 50-dimensional space and distance is super hard, right? Let's imagine 3 dimensions only, and there is a very, very cool tool where is used to dense those 50 dimensions down to only 3 dimensions, so we can visualize that into a 3-dimensional space. And when we go to king, which is on this bottom here, we see that very similar words, very close words, are queen, throne, sun. They are all in the same corner of this 3-dimensional space, right? And that's what embeddings, the power of embedding comes. It embeds, even do not only similarity searches and calculate distances, you can also do more advanced stuff. So for example, let's take king. Let's take the embedding of the word man and subtract it. We take the word, the embedding for woman, and do an addition on this, and we get a vector which is looking like this. And who is guessing what this vector is very, very close to?
Queen.
Exactly. So it turns out that it is we can not only use this for distance measuring, but we can also really calculate semantical meaning of one particular word. Isn't that amazing? But it didn't stop there. In all of these innovations we have right now with large language models, one of those early on transformer models is BERT, which is also an innovation by Google. And what it does, what is really good for, it is setting a word and it's embedding into the context of all words around. Because if you think only of a word-to-vec embedding, you would have words which are exactly the same strings. They have the exact same embedding representation. But we know as humans, language around, the context around makes the actual meaning of the word, right? And models like BERT use transformer models. They have this self-attention layer where they recalculate this embedding based on the context, which is not the content of this talk. But one other very cool thing of a BERT model is to be very close to those words, so we embed the contextual meaning of the whole sentence. But what a BERT model also does, it calculates one more embedding. And one more embedding, which is encapsulating the whole semantic meaning of the whole sentence into one embedding. So you suddenly don't have an embedding for each of the words, but also one additional embedding which encapsulates the semantic meaning of the whole sentence. And then we advanced again in research and some other foundational models. Google came up with a model called COCA. And COCA is based on an image-to-text foundation model where you don't only allow to put in text and a string as an input to calculate this or a sentence, a number of words to come up with this one embedding. A COCA model can also take a multi-model approach and use image information, so pixel information, as an input. And the very cool thing is that it maps both on the same vector space with the same embedded semantical representation. What does that mean? When we have a picture like this, and we feed it into the COCA model, we came up with a representation in a two-dimensional space with a point here. And if we would take another modality, like a string, like a dog in a grass field plays fetch with a red ball, this string, which has nothing to do with this image, maps to a very, very close point like this image, because the semantical meaning of both is very, very close to each other. And this is the power of multimodal embeddings. It's mapping different modality to the same vector space. And there are multiple use cases for that. We heard already today about RAG, so where you use that to search for relevant information, to augment your model prompt input with this information. But you can also use that for image search, where you don't have some notations on the images, where no one has a subtitle or a chapter for an image, and you want to search and make those those images searchable. But also recommendation systems, classifier, content moderations are great use cases. Let me show you a demo where we have, this is a public URL, so you can also use that, where this is used. So we have a database with products. All of those products, those are product images, they have no subtitle, they have no capture, there's no text behind those images, right? But we can search by text, for example, socks. And it embeds my input search key and do a similarity search to all the embeddings which we pre-calculated for all of these images. And you see, we have a couple of socks being ranked high. Those are ranked by similarity. And obviously this is just a word, but let's give it more context to see the power of it. So socks with stripes. So it even gathers the context of a striped socks out of an image, even without having any label data or key data. And we can do that on with stripes and being red. So all of these is searched by a vector embedding search and similarity search. Good. And even not being an AI engineer and not knowing about how those models really works in like how they are trained and how they build up, with Google Cloud and Vertex AI, you can utilize this power of these embeddings. And we have this unified SDK of Vertex, and easy as that, you can just load from a 3D model, which is multimodal embeddings, version 1. And then you can use that with just one API call here, where you input the image and you select the dimensions. And our API is allowed to give you an embedding with an embedding space from 128 to 1408. But you don't need to imagine that this is an Austrian insurance company which I worked on, so this is a real case. They process 20 million pages of customer email attachments every year on the purpose of retrieving identity cards. So customers, they scan a couple of contracts, and one page of this contract is, there is an ID card of any type on this image. And their purpose is to extract those identity card information. The problem is, you might know that, or you might imagine, hey, there are solutions out there. They tested for 3 years a couple of solutions out there in the world, and no one was good for them, because this Austrian insurance company, they had customers over all Europe, and the variance of ID cards which they need to process is so high that not a single tool can capture all of these types of ID cards. So they at some point said, we are building our own identity OCR tool thingy. And yeah, this is one example. Imagine a multi-page PDF document, average 20 pages per PDF document, and they want to extract structured data out of those embedded or displayed images. And it turned out that Gemini, especially the Gemini 2.0 Flash, is very, very capable of doing that. So what we saw in the demo beforehand, just feeding in the PDF document as an attachment, and then ask with they have a very advanced prompt with multi-shot, so example prompts, and the very structural approach, how to retrieve, for example, ID document ID numbers, because they have a very, very unique structure. Gemini was very, very able to extract those information with a very high accuracy. The problem, though, was the high amount of throughput. Not that our system can handle this amount of throughput, but in the end, it was the cost perspective. Because it turned out during investigation that it is way more suitable to take every page separately and do a prompt with Gemini. But imagine having a 20-page PDF file where only 1 or 2 pages contain ID cards. So you have 18 shots, so 18 pages and 18 very large prompts with a high volume of token numbers to Gemini, and you pay for them. The accuracy, the outcome was great, but when we deployed the software, it was way too expensive. So we came up with an approach by using embedding classification beforehand to pre-filter all of these stuff. So we utilize these multi-model embeddings. We take each individual site and create, by using this Vertex AI Python SDK, we utilize this Vertex API to come up with this embedding. And then what we build with this company is a relatively small fixture database. A database where we used roughly 500 different documents where we know they are actual ID cards. And you know what? You cannot just take example ID cards, because the most important thing is to store those example embeddings. You can use actual customer data for that. You can take your customer's ID cards where you know, hey, this is an example of, this is a document a customer already sent me. I can use this embedding and store this embedding without storing any PII data, because you cannot go back from an embedding back to the original image, and use this as a fixture. So we have a data set about 500 entries where we know this is a real ID card, a weapon shine of Poland, surfing license of a Portuguese person. So those are the ID cards they are handling with, by the way. And we have those classes. And then what we also did is not only having reference images in their embeddings, because we are multimodal, we can also have strings. So we described ID cards where we see errors, where we didn't filter those ID cards great enough. So for example, the scuba diving license. We added in this embedding fixture database as a reference, not only a scuba diving picture, we also had the sentence, an ID card of a scuba diver, as a contextual embedding of this string. Okay, then we have this fixture set, and what we've done is then a process for each page. We do a similarity search, and we calculate for all of these 500 fixtures the cosine similarity. We ranked them, and then we did some additional usage. We did a majority vote. So we took the most similar 10 fixtures and looked at how many of them are ID cards. Because you always have suddenly some very similar embeddings which are actually no ID cards, but if one out of the most closest 10 is no ID card and all the others are ID card, demonstrated that. We import the Vertex AI, and here, as said, as showed before, we can just use the multimodal embedding API from pre-trained, and then we have two helper functions where we get a text embedding for this text description fixtures, so scuba diving ID license, and one helper function for getting or retrieving image embeddings. And as you see, the main difference is just that you feed in as in the signature of getting embeddings the text, and here an image. Good. And then it is important to calculate the right, or to use the right distance algorithm. There are multiple ones, and there is really no, you need to use this similarity method to calculate the distance. You need to just try out which distance is best for your data. In our case, it was the cosine similarity. So here it is shown that this is kind of the angle between those points in a two-dimensional space, which worked out to be the best one. But there are multiple ones, the Manhattan distance, dot product, or Euclidean distance. You just need, you can ask Gemini to create a Python code for it, and then just try out and do parameter tuning by choosing one of them. And then here is this mechanism which I explained to you. We are getting the fixtures and the similarities of all the fixtures compared to our input PDF page. Then we look at the most similar one. So we rank them. We took the highest up one. If it's beyond the threshold, we instantly say this is the document type the fixture is from. If it's below a threshold, we say it's no ID card. It might be a dog or a tree or whatever. And then we did a majority vote. So we took the most up 5 votes and looked at what do these 5 votes, the majority of them, say what kind of ID document type it is. And those parameters, so this upper threshold, this lower threshold, and also the amount for the majority vote, we consider them as hyperparameters for our system. Since Fire to Gemini, we pre-filtered by multi-model embedding approach with this fixture set. And the cool thing now, after having that deployed in production for a while, they can increase this fixture data set with actual data which is coming in on the go. So whenever they classify or extract or miss an ID card, they track that. And whenever they see, hey, this, I don't know, climbing license from Switzerland, we don't detect that well, they take this real customer data, create embeddings, attaching that to their fixture data set, so that next time they can filter out that a little bit better. And by the end, we did a little bit of math. So they calculated 2 million pages, where about 10% of those pages only contains ID cards. One prompt which they sent for one of these pages had 8,000 tokens, because the prompt what they created is very, very extensively. It's a large one. This was necessary to come to the very, very good accuracy of all these metadata they wanted to extract, and they put a lot of examples of multi-shot prompts. And with Gemini 2.0 Flash, a token costs this amount of dollars. So one prompt costs them about $0.8 for each prompt. And imagine all these necessary prompts you do. Whereas a multi-model embedding API has a fixed cost, so one image costs exactly this amount of dollars, so a couple of cents. And another advantage turned to be out is that this prompt with these 8,000 token context on average takes 7 seconds. But the multi-model embedding API, only 2. So the throughput of the overall system increased a lot because they don't need that much time. It was a queuing system. So it was a queuing system where they picked every document, and they were now able to get down to the queue items in a much faster pace. And they save now nearly $20K dollars a year of costs only because of this pre-filtering. And that's why I believe GenAI is amazing, and we can do a lot of good things. And as an application developer, we can utilize that by using Vertex APIs straight away, and we don't need to really understand what's going behind those scenes. But other edge areas like multi-model embeddings, even for application developers, is a very, very cool and crucial tool to bring the overall application to a state where it's cost efficient and in a good outcome driven way. So that's why also for application developers you need to understand what multimodal embeddings is nowadays, and to utilize that not only in RAG applications but also for classification and search type of use cases.